Okay, this is the first video on switching logic. Switching logic is making logic functions out of transistors acting as switches. So first of all, I just want to recall what we covered earlier in the class when we went over BJT and Mosfet switches. Remember, here's your basic BJT switch, and Vin can only be one of two possible values. And here we're using 0 volts and 5 volts as our possible Vin values. Notice that the source here, VCC, is equal to 5 volts. So when Vin is equal to 0 volts, like we talked about, the collector to emitter would be an open. And if your collector to emitter is open, there's no current through this resistor RC. So it has 0 volts dropped across it, so that means that we have the same voltage on both sides. So the source voltage 5 volts, that's on the right side of RC, will also be on the left side, and that's where our node Vout is. So when Vin is equal to 0 volts, Vout is going to be 5 volts. Now when Vin is 5 volts, that's going to forward bias this base to emitter diode, and the collector to emitter is going to ideally act like a short, and current will flow through RC, and all of this 5 volts will be dropped across RC, because once the collector to emitter acts as a short, that connects this node V0 right to ground and makes it 0 volts. Okay, so you see that's our Vin and Vout table for the BJT switch. Now for the Mosfet switch circuit, and again, just like in a previous video, this is the N-channel enhancement mode Mosfet. So Vin again can only be one of two values, and we're going to use 0 volts and 5 volts again, and then the source value VDD, right, our drain voltage, or drain source voltage I should say, is 5 volts. So when Vin is equal to 0 volts, there's no channel, so the drain to source acts as an open, so no current through the drain resistor, so 0 volts across, same voltage on both sides, and Vout is going to be 5 volts. Okay, then when Vin is 5 volts, assuming that that voltage is much greater than the threshold voltage, well then the drain to source is ideally going to act like a short, so current will flow through the drain resistor, all this 5 volts will be dropped across it, and there'll be 0 volts at Vout since the drain is connected right to ground. So you see, whether you have a BJT switch or a Mosfet switch circuit of this type, you get the same relation between Vout and Vin, that Vout's always going to be the opposite voltage of what Vin is, right? Because there's only two possible voltages here at our input, 0 volts and 5 volts. So at the output, whatever the input voltage is, you're getting the opposite value. Okay, so 0 volts here, 5 volts, 5 volts, 0 volts, and same thing for the Mosfet switch circuit. And you see this is referred to as a not logic operation. Anytime your output is the opposite value of your input, we say that it's a not function. Okay, so in digital logic, we have all these various circuits that we're going to get to that perform different logic functions. And if you have a single transistor acting as a switch, you get the Not Gate logic function, or the Not logic function. The circuit's called a Not Gate. Also, the Not Gate is called an inverter. And here's the logic symbol. Okay, this is the digital logic symbol for an inverter or Not Gate. Okay, it's just a triangle with a circle. This is an input, or this is the input side. This is the output side. And often, well in fact all the time with digital circuits, we use what's called truth tables instead of tables that show the voltage levels. And often in these truth tables we use variables instead of Vin and Vout. We'll use just letters. So for example, if I use the letter A for input to this Not Gate, the output would be expressed A with a bar over it. And that bar is a symbol in Boolean algebra that means not. Okay, so you would say input A, output not A, and not just means opposite of. Okay, now before I forget, I made this little note here down at the bottom that on Polylearn there's a PDF that discusses Boolean algebra. Okay, I'm not gonna make a video specifically on Boolean algebra. I mean, we'll be using Boolean algebra in the context of other things, but when you look at this handout, what you'll see is that Boolean algebra is base 2 algebra, and a lot of the laws and identities are the same as base 10 algebra. There are some unique ones, such as De Morgan's theorem, that you should pay particular attention to. But make sure before watching any more videos past this video that you look at this handout. Okay, because like I said, we'll be using Boolean algebra the rest of the course within context of other topics. So the truth table for Not Gate would look like this. Put A here, and by convention the inputs are put on the left side typically of a truth table, and the outputs are put on the right side. So you see here's input A, output not A. Now in truth tables, instead of using voltage levels, we use zeros and ones. So here a 0 means 0 volts and a 1 means 5 volts. So the truth table for the Not Gate is just that whenever the input's a 0, you get an output of 1. Whenever the output, or excuse me, the input is 1, the output is 0. So you see this truth table is just a shorthand notation for these tables earlier that we wrote that had voltages. Okay, we're just using variables, letter variables along with zeros and ones instead of V in and V out along with voltage levels. But either one of these circuits, okay, a single transistor as a switch, will yield this truth table, and that circuit is being represented. Those transistor switch circuits are being represented by this circuit symbol. And you're going to see in the following videos that we can produce other logic functions such as AND gates and OR gates by using multiple transistor switch circuits connected up in various fashions.